Okay, this is a review of GABA agonists. Understand anxiolytics and anesthetics. In order for us to understand the agonism of GABA, we also have to understand what normally happens in the body through standard stimulation. So, picture of something familiar with already. And let's just say, for the sake of simplicity, that we are talking about glutamate. The most common excitatory neurotransmitter, something that's going to prompt action potentiation. And here's an NMDA receptor, which is a glutamate receptor found in the brain. And when the glutamate binds to the NMDA receptor, a channel is open. To understand what happens after that, we need a little bit of the background. So we know in general that neurons tend to be slightly more negative. Actually, all cells tend to be slightly more negative than the surroundings. And this is just relative to the surroundings. So on the inside, we can illustrate that by putting some negative ions. The outside, we'll put some positive ones. Now, once again, this is all just relative. And the reason why they're positive is because of the ions that are out there. So, for example, let's draw some sodium ions. On the inside, let's also draw some sodium ions, just not as many. And let's also illustrate it graphically by showing where the membrane potential is. So let's try writing up here where there's some more room. Membrane potential. So without stimulation, we start here at rest, and that's why we refer to this as our resting potential. And essentially, this illustrates the electrical characteristic of the neuron, inside the neuron versus outside. So like I said, because it's more negative on the inside than the outside, the resting potential is going to be down here at the negative area. And so what happens is when the NMDA receptor is bound to by glutamate neurotransmitter, the sodium channel opens up, and this is what we call voltage-gated channel. The sodium then will flow in because there's a higher concentration of sodium on the outside than there is on the inside. And so therefore the sodium ions flow in, and it's not because the positives are trying to get to the negatives, it's because there's more sodium on the outside than the inside, so you have diffusion of high concentration to low concentration. But as a result of the diffusion going in due to differing concentrations of ions, because they're positive, the membrane potential goes from the resting potential and becomes more positive. So as the sodium ions are starting to pour inside here, what ends up happening then is this membrane potential starts becoming more positive. Now, it goes past zero because the point is not for it to become neutral, but to make sure that the number of sodium ions inside and outside, in terms of the concentration, that one little area is going to be equal to one another, what we call dynamic equilibrium. So in this case, in order to make it even, it actually goes more positive than zero. It goes up somewhere there. Now, there's more to that picture, but that's all we need to know for now. And then, of course, there is a thing called a threshold. And threshold I defined earlier as the point at which the membrane potential needs to be in order for an action potential to be fired. So essentially what happens is, as as soon as this action potential is fired, the sodium ions have poured in, it's become more positive in this area. Well, let's just change it now to becoming more positive. What ends up happening then is the positive charges are going to activate other channels here, sodium channels, that are still kind of negative on this part because it's not quite reached it yet. Sorry. Still kind of negative in this area right here. It activates these things to open, and once again, because there's a higher concentration of sodium on the outside, they start flowing in, and these parts become more positive, and so on and so on. And so there's a cascade of membrane potential changes as this moves down the neuron. So this happens because there's more receptors and more channels along, not receptors, more sodium channels along the way, and it's a cascading domino effect. And that movement of negative to positive is what we refer to as the action potential as it moves down the neuron. Now, if, for instance, you do end up with a stimulus that's not quite as strong, then it's very possible that you will end up it going more positive and not quite getting to action potential. Here's another attempt, and action potential is not fired. You need a significant amount. And so whether that's anxiety or waking up or being aware or remembering or feeling pain, all of this has to have enough of stimulus to hit the threshold for the action potential to be fired. Okay. Now our point is that individuals that have great amounts of anxiety or people that are going to surgery because of the great deal of pain, we want to try to reduce that resting potential such that when they do feel that enormous stimulus, it doesn't quite hit threshold. And this is the idea of GABA. So on the next page, what we'll see is, in this, you can go back and do this with the website, the McGill website that's on the review sheet, where it shows how benzodiazepines work, so you can go through that, but I'm going to show you the basics of GABA works, and then you can figure out benzos from there. Once again, let's just say that we have a receptor here, but in this case, this receptor is a GABA receptor, and because it's GABA, it doesn't allow sodium to come in, but rather Cl minuses. So we're assuming that there's more Cl minuses on the outside and the inside. So when GABA binds, Cl minus flows in. Once again, more negative on the inside than the outside. And you might question yourself and say, well, wait a second, why, if there's more Cl minuses on the outside, then shouldn't it be more negative on the outside? Well, understand that there's a lot of other ions in place, including sodium ones, and there's a lot more sodiums on the outside than there are chlorines. And so net effect is that it ends up being more negative on the inside. But anyway, focus on the fact that there's 3 Cl minuses on the outside, 1 on the inside, and you see that this then will flow in when GABA is bound to by GABA neurotransmitter. And so if you look at the graph again, and this is the resting potential, let me just replicate what happens when sodium flows in. When sodium flows in, this thing goes up again like that. Maybe it hits threshold, and we'll say threshold is right here. But in this case, because chlorine has gone in here, it lowers that resting potential to down here. So this is where due to GABA. Okay? So because of GABA, it's further down here, and when the action potential is fired at this point, even if it's the same amount of stimulus, the same thing that would make you anxious, same thing that would make you wake up and keep you awake, the same thing gives you insomnia, the same thing that makes you feel pain doesn't quite hit the threshold and action potential is not fired. this is how it chills you out essentially. Now, in a case where, let me see if I can do this. Nope, that's not it. Okay, anyway, in the case, I can't really show it here because I can't cut and paste this. Oh, there we go, perfect. So in the case where you would have like a benzodiazepine, at the benzodiazepine, you can imagine what happens there if it makes GABA more efficient. When benzodiazepines or any GABA agonist binds to GABA and does what GABA does, it helps GABA do its thing even better. It may increase the frequency of GABA frequency of Cl minuses flowing in, or it might increase the duration of the Cl minuses flowing in. The bottom line is it further reduces the resting potential. So here you go. So you got GABA, which normally is going to chill you out, but then you have a medication that will even bring you even further down, and therefore no chance of waking up, no chance of feeling anxiety. But then also there's a greater chance of overdose as a result of that, lack of respiration for things that do affect GABA in those sites within the brain. So, within the brain that controls, breathing. And so this could be due to alcohol or anesthetics or anxiolytics. And that's why it's really important, that's why it's really important not to take these in combination with one another, because they work off of one another. And also depends on which part of the brain. Is it a part of the brain that really affects vital function? And the way we know that is we look at overdose reports. Anxiolytics, we see very little people overdosing in anxiolytics. We see that more with barbiturates like sodium pentothal. We see that more with propofol. We see that with alcohol. So we know in those cases the site for these particular drugs are found in GABA receptors inside of those critical brain function areas, whereas benzodiazepines, and we'll learn later on, like non-benzos, not as much.